Section 7.7 is about writing exponential functions. So we're going to be using these exponential functions to model real-world application type behavior. So just as a reminder, we've got an intro here that reminds us of the general form that exponential functions tend to follow. Y equals a times b to the x. A couple of important pieces of this general form. It contains an x and a y. Well, that's because we're talking about a function. Remember, functions have x's, which are our inputs, and y's, which are our outputs. You put in an x and you get out a y. So there should be x's and y's in your functions. There should be variables. A and b, however, those are not going to be variables. Those are going to be actual numbers. So you might have something like, y equals 2 times 3 to the x, for instance. So we will have some letters, x and y, but you shouldn't have a ton of letters floating around in these problems. So this is just a general form to keep in mind. And exponential functions tend to model a lot of real-world situations. Two of the key words we've used a lot when we're talking about exponential functions are growth and decay. Many real-world situations involve growth or decay. So we've got some examples here of things like population growth, radioactive decay. Radioactive decay refers to how long it takes for radioactive elements to denature themselves. So things die over time, they decompose, they split apart, even atoms and molecules. And certain radioactive chemicals will have basically a certain lifespan. And over time, they start to decay just naturally. And radioactive decay is a measurement we can use to tell how old something is. Or things like interest accrual or asset depreciation. So all of the words I underlined are important words that contain meaning. Growth and decay, hopefully, are obvious, but accrual and depreciation, these are accounting terms that you might not use very much in your everyday life. To accrue something means to gather it or to gain it. So if I accrue a lot of interest, I'm gaining interest. So that would represent growth. If something is depreciating, it is lessening in value. So it's lowering in value, or another way to say that is decay. So we're going to be dealing with problems where you might see words like, interest accruing over time or asset depreciating over time. You will actually need to know what those words mean. You will need to know that to accrue means to gain or to grow, and to depreciate means to decrease or to decay. So you might not be looking at word problems where we use words like increase, decrease, growth, decay. We might be using other words like accrual and depreciation, and you'll need to know what they mean. So I know this is a math class, but in this particular unit, you might need to use a dictionary. If you see an unfamiliar word and it seems like it involves something with maybe accounting or something like that, and you don't know what it means, we might have to look it up. So please don't shy away from using Google or something to figure out what a word might mean. All right, so what we're going to do is we're going to take a look at a real world example and we're going to model it using an exponential function. So here is a real world example for us. The population of students at Cooper High School is currently about 1,400. That's true. I think we've got like 1,370 something, somewhere in that ballpark. So we're going to round it and just say it's about 1,400. And our student population is growing at the rate of about 1% per year. That's also true. Our school's getting bigger. We're getting new students every year, getting just a little bit bigger with each incoming class. So this is a real world situation, and we're going to model it using an exponential function. So we need to figure out what our x and our y are going to be. And we give this to you in the problem. We're going to let x equals time, and specifically by time we mean the number of years. Okay, so we could measure time using, years, months, weeks, days, minutes, hours, seconds. We're measuring it in units of time, in units of years. Now we're going to let y equal the number of students at Cooper, just number of students. Our goal here, our first goal, is to create a table that represents the student population over the next 4 years. So we know it's growing. It's growing at the rate of about 1% every year. How are we going to figure out how many students we have in each of these pieces of our table? So let's start with our first x value. Our first x value is 0. Well, you wouldn't say year 0, so to speak. What we're really saying here is that no time has passed. So it hasn't been any years since this problem started. So our number of students is going to be whatever our starting value of students was. And that's always given to us in the problem. So the problem here says our starting value or our current value of students is 1,400. So we can just plug that right into our table without thinking too hard about it. But here comes the math. To go to the next year, we have to figure out how to add 1%. So can anybody think of how we would figure out what 1% of 1,400 is? If you had to find 1% of something. Rebecca says multiply by 0.01. That is perfect. That is exactly what I would do. So 1%, we could think of that in multiple ways. 1% is a fraction, 1 out of 100, or it's a decimal, 0.01. I prefer to think of percentages as decimals, and the way I do that is if I've got 1%, I take the decimal on the 1 and I shift it over to the left 2 places. So it becomes 0.01. So that's how we're going to think about it today. So we need to add in 1%. Oh goodness, we need to add in 1% or 0.01. So Rebecca nailed it. We want to multiply 1,400 times 0.01. And you can use your calculator for this. So if you punch that into your calculator, you get 14. But 14 isn't what goes into the next box. You don't go from 1,400 students to 14 students. 14 students is how many students we're adding for the next year. So we have to actually add the 14 plus the 1,400. So you get 14, 14. So real quick, I'm going to take a moment to point out how we go from 1,400 to 1,414. We essentially added 100% plus 1%. Or another way to think of it as 1 plus 0.01. Well, 1 plus 0.01 is 1.01. So here's the moral of the story. To get from 1,400 to 1,414, we multiply by 1.01. I'm going to zoom in just a little bit. We're multiplying by 1.01. This 1 here represents the original 100% that we had, and that 100% was just the 1,400. And then the 0.01 is the new 1% of students that we're adding in. By multiplying by this number, we get to our next number. So try that out on your calculator. Type in 1,400 times 1.01, and you should get 1,414. So we've kind of condensed this process a little bit. I can erase a lot of these notes. To get from one step to the next, we multiplied, so times 1.01. Now we're going to go from year 1 to year 2. To go from year 1 to year 2, we're going to add in another 1%. So we would have the 100% of students that we had in year 1, so 1,414, plus the new 1%, which would be 1.01. So we're going to multiply again by 1.01. Punch that into your calculator. 1,414 times 1.01. And we get a decimal number. This model is attempting to predict how many students we're going to have. So we're going to get some weird stuff like decimal numbers. You can't have a fraction of a student. So obviously decimal numbers are not going to be completely accurate here. But we'll worry about rounding later if we have to answer questions about students. So for now, just for the purposes of getting our table in order, we won't worry too much about rounding these yet. Do you guys see a pattern? To get to the next one, we're going to have to multiply by 1.01. So 1428.14 times 1.01. That gives us about 1,442.4-ish. And one more time, we're going to multiply by 1.01. And I get about 1,456.8, we'll say. So these numbers are obviously not super realistic. We're never going to have fractions or decimals of students. But this gives us an idea of about how many students we can expect to enroll at Cooper each of these years. So we're going to answer a few questions about this function now that we've got an idea of what our table looks like. The first thing we want to do, or I guess the second thing we want to do, is graph the function. So we're going to actually take these points and we're going to plot them on the graph. So let's start with 0, 1,400. That'll be right here at this intersection. I'll make my point a little bigger so you can see it. 0, 1,400 would be right there on the axis. Our next point is 1, 1414. So that'll be about here. So a little bit higher than halfway through between those 2 points. Then 2, 1428. Might have drawn that one a little too high. Just trying to get these close. 0, 1442, or I'm sorry, 3, 1442. And 4, 1457-ish. I didn't do a great job of getting these points in the right spot, but they look close. So, the third question is, what kind of function does this model? We know 2 types of functions that we've learned so far this year. Only 2. We know linear functions and we know exponential functions. Just based purely on the graph, what does this look like? A line or an exponential? Just based purely on the graph. It looks like a line. Is it a line? Any thoughts? Remember what we talked about last week about the change in y values. Our pattern that we're changing by on our y values here is multiplication. We're multiplying by 1.01 each time. So that's a multiplicative pattern. Does that make this a linear or an exponential function? Anybody? Exponential function. Thank you, Joel. An exponential function. So that was hopefully a dead giveaway because this entire packet is called writing exponential functions. That's what we're doing here. But even though it looks like a line on our graph, this is not a line. So I'm going to do my best. I didn't draw these dots in like the exact perfect place. They're kind of going like this. So what we've done is we've looked at a really, really small section of a much, much larger graph. Much, much larger graph. So this line is going to keep going this way for a long time, but then eventually it's going to kind of curl up like this. And the same with the other side. This side's going to keep going down like this for a long time, but eventually it's going to kind of curl and flatten out. So we're just looking at a really small piece of this graph. And because it's such a small piece, it kind of looks straight. But really, this is a big curved graph. And we'll take a peek at Desmos here toward the end of class, and we'll look at that together. So our answer to number 3 is exponential. This is an exponential function, and we need to explain why. The reason is because the y values change multiplicatively. This should ring a bell. We talked about this last week. When your y values change using a multiplication pattern, that's when you know you have an exponential function. So now the real fun comes in number 4. Number 4, I'm even going to highlight this. Number 4 is what most of your examples are going to look like this week. You're going to be given a situation, and you're going to have to write the function itself. You won't have to make a table or make a chart or draw a graph or just, explain what type of behavior it is in most other problems. What you're really going to be doing is number 4, finding the exponential function that models the situation. So here's how we do that. What I'm about to write down, you do not need to include in your notes. So I'm going to write something, but then I'm going to erase it. Think about what we did to make our table. First, we started with the number 1,400. That was our starting number of students. Then, for each subsequent year, to figure out how many students we were going to have in the next year, we multiplied it times 1.01. Then to figure out how many students we were going to have the next year, we multiplied again by 1.01. Then for the next year, we multiplied again times 1.01. And we just kept repeating that process. If I wanted to know how many students we'd have in year 10, I would multiply 1.01 in 10 times. So this is a pattern that kind of repeats itself. And that's going to help us. Well, what's another way to say 1.01 multiplied to itself that many times? 1.01 to the power of x. So that's going to be our answer to number 4. So this part you do want to write down. Our function is y equals our starting value times our factor, 1.01, to the power of x, where x is our number of years that we want to look out into the future. So the next question, question 5, asks us to make a prediction. According to our model, how many students will Cooper have 20 years from now? How would we solve this? Well, the key word here is 20 years. We are representing years with the variable x. So all we have to do is put 20 in for x, and you can use your calculator for this. In fact, you absolutely should use your calculator for this. So we're going to plug 20 in for x, and that's going to give us a lot of students. 1,708. So think about this. I mean, the people who run this school have to make decisions, have to make long-term decisions about the sorts of services we provide on campus. You know how we've got some mobile units in the back? Well, how did they know they were going to need those mobile units? They used a formula like this to figure out how many students we were going to have the following year or the year after that, and said, you know what, if our population keeps growing the way it is, we're going to have 1,700 students in 20 years. Maybe we need to add a new wing onto the building. instead of, mobile units. So we can use formulas like this to make decisions, to predict things that are going to happen. Now, no predictions are perfect. So in the real world, patterns can change. Things can happen. For instance, if a new school opens up down the road and they take a bunch of our students, like what happened when Cooper first opened up 10, 12 years ago, that could decrease our population. And so instead of continuing to go up, our population could dip way down. Or maybe right now a lot of people are moving to Northern Kentucky. And so our student population is going up, but maybe that'll slow down after a while and we'll stop growing so fast. So that can happen too. So this is just a prediction. It doesn't mean it will happen. It's just a pattern that we've noticed, and we're deciding, okay, if the pattern continues, here's what will happen. And you can look out into the future, 20 years, even 100 years, and look and see if the pattern continues, what the student population would be like. So this was a fun example to actually think about our school and how many students are here. But what we're going to be doing is using this type of process to answer tons of different types of word problems about everything from population to the value of a car to how long your REM cycles last, right? So there's a lot of different types of problems we can model with exponential behavior. This problem was exponential growth. Some problems, though, are going to be exponential decay. And we're going to write down some generic formulas that are going to help us in these problems. So here's our formula for exponential growth. We will discuss this in great detail and break down each little piece, but you'll want to write this down. Y equals A times the quantity 1 plus R to the T. We will talk about this bit by bit. So Y here represents the amount or the population or the value, whatever the current amount is. And unfortunately, I can't get any more specific than that. I can't tell you what it's an amount of because every problem is going to be different. In the example we just did, Y was the number of Cooper students. But in other examples, it'll stand for different things. So just think of Y as your current amount of something. A is your starting amount. So if we look back at the example we just did, our A value was 1,400. That was the number of Cooper students that we started with in the example. That was our starting amount. R is our rate of growth or decay. And in the example we just did, what was our rate of growth? 1% is the rate. Rates are always percentages. So I want you to make a note of that. Rates are always percentages. So if you're given a percentage in the problem, you're dealing with a rate. Now that's very important because there will be problems where you don't get a rate, and we'll talk about those in a second. Finally, we get used to using X's and Y's, but then in the example I just gave you of exponential growth, there's no X there. In most exponential growth problems, we will be talking about something growing over time or decaying over time. So instead of X, we use T. So I'm going to put in parentheses here. This is basically our X value. That's our X value, but we're going to call it T, and it stands for time. So let's go back to how we built this exponential growth model. So in our previous example, our starting amount of students was 1,400. And then we took 1 plus our rate, which was 0.01, and then to the exponent of time. So however many years we wanted to put there, we would put in for T. And this is how we built our model. Now, notice the 1 plus 0.01, we would actually add that together, and we would write it as 1,400 times 1.01 to the t. But I wanted you to notice that the 1.01 is made up of 1 plus 0.01. That's where it came from. It came from the 100% that we started with plus the 1% that we're adding, the 1 plus 0.01. Okay, so pay attention to things like that. This is what exponential growth looks like. Exponential decay is very, very similar. The only difference is instead of a 1 plus r, we'll have a 1 minus r. Everything else is identical. Make sure you get this written down. You'll want this too. So if we had an example that said, Cooper student population decreasing by 1% each year. So now we're going to flip it up on its head. Instead of our Cooper population increasing by 1% each year, we're going to pretend like it's decreasing by 1% each year. That would give us 1,400 times 1 minus 0.01 to the t, which would be 1,400 times 0.99 to the t. So now you see the difference between adding 1% and subtracting 1% each year. I do want to remind you of one thing. You know those growth and decay models we've been talking about? Growth is what you get when your base is bigger than 1. So over here, our base would be bigger than 1. This is growth because we're taking 1 plus something. When you take 1 plus something, you'll have a number that's bigger than 1. So that's why you have exponential growth. But with decay, over here we're taking 1 minus something, so you'll end up with a number less than 1. That's why you end up with decay. Your base less than 1. So I know I'm throwing a lot of notes at you here. The moral of the story is, despite everything I've written on the page right now, really the only important stuff is right here in this box and maybe just below the box. This is the good stuff. This is the stuff that you're going to need to answer every single question. You're going to want to know your exponential growth formula here and your exponential decay formula here. We're going to use this to do tons of examples tomorrow and Wednesday and Thursday, and then again on your quiz on Friday. So just a few more notes I want to make. One is to bring this back around to our generic form. Y equals A times B to the X. The thing is, exponential functions will have a base. Our base is a little more complicated now, though. Our base is made up of some other things. Our base is made up of 1 plus a rate or 1 minus a rate. So if you're given in a problem, you're going to want to write this down. In the problem, if you're given a rate, you will have to, absolutely have to, find 1 plus the rate or 1 minus the rate to use as the base. That's if you're given a rate in your problem. And you'll know it's a rate because it will be a percentage. On the other hand, in some problems, you will not be given a rate. You will be given a factor. If you are given a factor, You just use the factor as the base. And you might be thinking, what in the world does that look like? I'll give you an example in just a moment. As soon as students are done writing, I'll write up an example. So if we were going to redo the Cooper problem, I'm going to write it a slightly different way that would use a factor instead of a base. So this might say, Cooper has 1,400 students currently, and they're increasing by a factor of 1.01 each year. So if the problem started out this way, Cooper has 1,400 students and they're increasing by a factor of 1.01 each year. Notice what I did. I cut out the middleman. So the reason we use 1 plus r is to find that factor. We take 1 plus 1% or 1 plus 0.01, which gives us the factor of 1.01. But in some problems, they will straight up give you the factor. So you don't have to do the steps of using the 1 plus r. You just plug that straight in. Okay, so I just wanted to point that out to you because on some of the problems that you'll encounter, you'll get a rate and you'll have to put that in to find the factor. On some problems, they will just give you the factor and you just use that as your base. You don't have to do all the other gymnastics to figure out what that is. But I thought it might be cool to actually look at the graph on Desmos. So we came up with a formula for students at Cooper over time, and it was 1,400 times 1.01 to the power of x. And so I just want to look at this on a graph. If we zoom way out, there it is. Now you can see that it's an exponential function. When we were looking at the graph, we were just looking at kind of this little section of it right here, which looks like a straight line. But if you get the whole graph in your picture, you can clearly see this is not a line. This is an exponential curve. And notice that as you read it from left to right, it goes up. That means it's a growth function. We could also figure out some other things about it. For instance, what's our y-intercept? We can scroll way in and you can see it pretty clearly. Our graph crosses at the point 0, 1,400. Go figure, right? 1,400? That number should sound familiar. That was our starting point. That was the number of students we began with. So at time 0, at our initial time, before any time had passed, our y value was 1,400. So these things should all seem like they're starting to tie together now. One of the other things we talk about a lot with exponential functions is our asymptote. Remember, the asymptote is a horizontal line that our function is getting really, really close to. So look here, our function is getting really, really close to this line. Any thoughts about what that line is? That's our axis. That's our line y equals 0. So we have an asymptote at y equals 0. And remember, our function will keep getting closer and closer to that line, but it'll never actually cross it. It'll never touch it. So the further we go left, the closer it gets. And if it starts to look like it's getting really, really close, all we have to do is zoom in more, and you can see we're actually not there yet. We'll get closer and closer and closer the more left we go. We're getting closer and closer, but we're never going to touch. And as soon as it looks like we're getting close enough to touch, all you have to do is zoom in and you'll see you're not quite there yet, right? That's how asymptotes work. So hopefully these different features of exponential functions are starting to kind of tie together, starting to feel like they're making sense to you. Think about these things when you're dealing with these problems. What does that mean about our student population at Cooper, for instance? Think about how these different concepts tie in together. So just a little fun with Desmos. As you're working with problems like these, feel free to use Desmos. Play around with it. Look at these functions on a graph. Find your y-intercepts. Find your asymptotes. And see if you can figure out what that says about the problem that you're working with.